One type of series that you will see a lot is what is called a p-series. And a p-series is anything in this form. It is 1 over n raised to any power. So it could be 1 over n squared, 1 over n cubed, etc. A special type of p-series is when that p is equal to 1, 1 over n is sometimes also called the harmonic series. But you can call it a p-series as well, but a special name for it is just the harmonic series. We want to figure out, because you'll see this type of series a lot, 1 over n squared, 1 over n, 1 over n cubed, I want to come up with a general conclusion for what happens for different values of p. And what we're going to do is we're going to prove these using the integral test. So first one is what happens when p is equal to 1? So that would be this, 1 over n to the first. So I'm going to go ahead and use the integral test. So using the integral test, I'm going to rewrite it as an integral from 1 to infinity, oops, if this is our series, of 1 over x dx. The antiderivative is, I'm going to rewrite with the limit, natural log of x from 1 to t, plug in my bounds, so natural log of t minus ln of 1. This I know is 0. Natural log of infinity is infinity. So we're going to say that because the integral diverges, we can say that this p-series, or it's a harmonic series, also diverges. So from now on, anytime you see 1 over x, you don't have to prove it using the integral test. You can just tell me it diverges because it's a p-series or a harmonic series. We did the proof right here. Okay, now let's see what happens if p is greater than 1. So we're looking at this scenario. Oops, n to the p, where p is 2, 3, anything bigger than 1. So if you see 1 over x squared, 1 over x cubed, what's going to happen? So we're going to do the same thing. We're going to apply the integral test to this. So 1 to infinity of 1 over x to the p. And I'm going to rewrite it with the limit statement again. And I'm going to rewrite this by bringing it to the top. So when we have an exponent on the bottom, I can rewrite it by bring it to the top, and it's the same as x to the negative p. And this is going to go ahead and allow us to do our integration. So this is just really your power rule. So I haven't taken the antiderivative yet, so let's go ahead and do that. So how do we take the antiderivative of x to the negative p? This is just your power rule, so we're going to go ahead and add 1, divide by the power. Let's plug in our bounds. So I have limit, as t goes to infinity, the x becomes t. I'm going to subtract off what happens when I plug in the 1. Okay, now let's take this limit and see what happens. Okay, this part right here, regardless of what p is, this is going to be a number. Right? It doesn't matter what the p-value is. For any p greater than 1, this will always be a number. This piece right here, when p is a number greater than 1, let's think about what happens. So let's pick a number bigger than 1. If I plug in like 3 here, notice you will have a negative exponent on the top when you add that 1. This will still be negative. So what's going to happen is the t is end up going to the bottom. So if infinity is on the bottom, what happens is this fraction will go to 0. So this is going to go to 0, this is going to go to a number, so the whole thing will be a number of some kind, so we're going to say that this integral converges. So if the integral converges, we can say that this series converges. Okay, now let's look at the scenario when p is less than 1. Now we're still going to look at this because the antiderivative doesn't change. We're just going to think about what happens if p is a number less than 1. So let's try 1/2. Again, this is still going to be a number. That doesn't change. But if this is a number less than 1, a number less than 1, negative like 1/2 plus 1, the t is going to stay on the top. So that means when I plug in infinity, this fraction will actually now go to infinity. So infinity plus or minus any number is still infinity. So this is going to diverge because this is going to diverge. So this is our 3 cases for the p-series. If you have 1 over x, that is going to diverge. If you have 1 over x to the p, Where p is any number greater than 1, it's going to converge. If you have 1 over x to the p, or n, this is going to diverge as well. So now that we've proved it, you can go ahead and just use this anytime you see or recognize a p-series. So now when you see this series, you don't have to prove it using the integral test. You can just tell me this is a p-series, and we learned that this diverges. Done. Same thing here. This is also a p-series. The p is bigger than 1, and we learned that this converges. Done.